All right, so yesterday we found out that, and this will be the third time for a lot of you, that when we're doing powers of 10, don't sit there and act like, well, this is the third time I've had this, so therefore I'm not going to learn anything. It's possible that you had gaps. You might have had gaps in the first time you learned it, especially as a 10th grader. 11th grader should have been stronger, and then by now it's like I could teach this. If I go to college and the word comes up megamoles or millimoles, it's not going to bother me. And none of that's going to bother me. So I think that's one of the keys to starting off in a science class too. Every science class I've ever seen has some relationship to powers of 10. Okay, do you have any questions on this sheet as far as, you shouldn't have to recreate the sheet. It should be kind of in your mind. My own opinion is that it should be in your mind kind of like this. It's kind of like a series. Thank you. I think it should be, if I were going to practice this, I take a sheet of paper out and I just make a bunch of steps like this. And I might start with 10 to the 12th and go all the way down to 10 to the minus 12. And then without looking, see how many of these things I actually remember and said, you know what, I think I mastered it. That's one of my goals for you this year, is that you don't just do this. You say, I've got this now. I've mastered it. And it takes a little work, doesn't it? All right. So if you were to memorize it this way, then you could quickly in your mind, I mean, you don't have to draw this out. You can actually do it in your mind and say, I can make that conversion. And this is metric to metric conversion, of course. So let's try one. And remember, there were 3 ways that I said we could do it. And you can decide which way is best for you. Let's try, let's do, how about this one? 360 angstroms equals how many microns? Okay. So way number 1, method number 1 is the underhand serve. It's going to go over the net, and you're going to get it right. But it's really not what a senior should do, okay? And certainly if you're in college, I'm not saying you can't. You can't. But let's take a look. Angstrom is what, where am I at? What power of 10 is that? And we didn't write that here because it wasn't a prefix, but an angstrom is 10 to the minus 10 meters. Is that right? So we started at angstrom, we're going to microns. What's a micron, Parker? Let's see if you remember that.
10 to the minus 9.
What is it?
10 to the 6, negative 6, minus 6.
Meters. Remember that a micron is not a micro. Micro is 10 to the minus 6 anythings.
Yeah.
Micron is 10 to the minus 6 meters, isn't it? It's a distance unit. So it's true, we're going to the same place micro is, but it's where micron is, right? So here's angstrom. You go 1, 2, 3, 4. I saw my finger go 4 steps to the left. So I take the number 360. Yeah, it has a decimal. And I make it go 4 to the left. And there's no way that I'm going to miss that if I want to use that method. You get it? So let's do it without having the sheet in front of us, okay? When I think of angstroms, what power 10 do you think that is again? 10 to the what?
Negative 10.
And I'm going to 10 to the negative 6, right? Let me ask you this question. Am I going from, I have a lot of little things going to bigger things, or I have a big thing, I wonder how many little things it is? Which one is it? Which one is this? What's an angstrom compared to a micron?
Very little.
So I got a lot of little things, right? Is that going to be a lot of these big things or lesser? Isn't it going to be a lesser number? It's going to be a smaller number. So I know the number's got to shrink. How many powers of 10 is it going to shrink? 4. So all I do is make the number 4 powers of 10 smaller. And you move the decimal both ways, you'll figure out one of them makes it smaller. You get that? So that's number 2. Number 3, I want you to pretend that this number, like in many science books, would have been written like this. And now we still use the same idea. I'm going from angstroms to microns. Got to get smaller by 4 powers of 10. So, Marie, how do you make that number smaller by 4 powers of 10? What is it?
10 to the negative 2. Or, yeah, 3.6.
Okay, and take a negative 2, right? But we said the answer is this. Which one's right? They're both right. So, if you can do it 3 ways and you get the same answer, you should feel more confident like that. I know some of you, if I were to give a quiz or something, I know you're going to want to use the finger method because you feel very comfortable with it. I'm asking you to move to the next comfort level and see if you can jump a little bit higher and make it a little bit easier for you, okay? What do you think? Pretty easy? All right, let's move on. And again, this is review, and they're going to have this. If you go to college, and they'll have a chapter on measurement, and they'll have numbers on it, and they'll have powers of 10, and they'll have scientific notation, and the professor is going to say, I know you had this, and they're not going to spend a whole lot of time on it. So you got to get it down now. You say, I got it. You'll never have to teach this to me again. I have it. All right. Now, scientific notation. I was taught, and I mentioned this to you before, I was taught the way they do it in a math book. I was taught the way they do it in a lot of science books. I've seen a lot of science books, and they have rules like this. And these are very concrete rules. What's the problem, though? What's the problem with having these steps? Hey, it's got all the steps. You're right. It tells you exactly how to do it. So why do I think you shouldn't learn it that way? Anybody think about that? What? Here it says, move the decimal so that it's only one digit to its left, and it says 6 places. And then it says here that if you were to move the decimal left, then it becomes what kind of an exponent? If you move to the right, it becomes a positive or negative exponent. See that? Do you bet $100 you know which one that is? If I move that decimal to the left, do I replace it times 10 to the negative something or positive? You lay down a $100 bill right now and say, I remember it? Maybe. So what I think's wrong with this is that if you have such a concrete way of doing this and you mix it up, you'll miss all of them. If I say do 5 of these problems and you said, oh, I thought if you moved to the left, what? Why did you say, if I thought I remembered this correctly. Well, you miss them all. We don't want to do that. So the approach I was trying to get you to do last year is something like this. Remember that first page on this handout sheet? What did all the numbers that had positive exponents have in common? What do they all have in common? If they have a positive exponent, what do they have in common? How about the ones with negative exponents? What do they have in common? What do you think? Jeff, you got an idea? If you have a positive exponent, 10 to the first, 10 to the sixth, 10 to the ninth, what kind of number are you?
I don't know what to say.
It's one or larger, isn't it? It's 1 or larger. What about negative exponents? What do they all have in common? By the way, every number on this sheet is a positive number. 10 to the minus 6 is not a negative number. It's not a negative number. You get that? So 10 to the minus 6 and 10 to the minus 9 and 10 to the minus 2 have something in common. What do you think? Clayton, what do you think have in common? What all the numbers have negative exponents. They have something in common with each other.
Less than 1.
Less than 1 negative? Or less than 1 what?
Less than 1.
They're decimal numbers, aren't they?
Yes.
Where do you find all these numbers? Everybody know on the number line? If somebody made a number line, say, where do you find 10 to the minus 1, 10 to the minus 6?
Between the 1 and the 0.
Very, very, very good. We never do cross into the negative numbers, so they are less than 1, but they're greater than 0, aren't they? So I think you know that. So here's what I want you to do, right? I think this is the best way to do this. I look at that number there, and you know that if you can make that in scientific notation, it's a decimal number, right? I might as well put that there. This is a positive number. I mean, 1 or bigger, I'm sorry. This is a decimal number, right? I might as well put that there. Now, decimal number. I might as well just do that now. Now, you see that? That was pretty simple, wasn't it? Now, I'm not going to get fooled, and I'm not going I'm not going to say 10 to the minus 6 when it should have been 10 to the 6th. I'm not going to do that because in my head I already know it. I have a way of catching it. I better have a negative exponent there, right? I already know it. Now we're going to move the decimal to create a number between 1 and 10, not counting 10. And so let's take a look. Hey, almost 0.5? No, that's not between 1 and 10. So 5, I got you. Okay, 5. What are you? 5.05 and 8 and 1 and 1 and 2.5. Okay, most people can do this. This is not the hard part. Are you okay? And then we have one more thing to do. How many places did you move? Don't say left or right. How many places did you move that decimal? I put it 1, 2. I moved it 3 times to get that number 5. Here I moved it what? 1, 2, 3. And okay. And here I moved it 1, 2, 3, 4. This is so. I wish somebody would have taught this to me, because here I am. I remember saying, "Oh, do I remember that? Do I remember that rules? I remember all those rules," and I don't have to do that. One place. All right, what do you think? Is that pretty simple? All right, so now let's do a couple more. I'd like you to do. How about doing? Oh, I don't know. Why don't you do 5 random ones? Okay, do 5 random ones here and try to make it hard. Make it hard on yourself. Do you need a handout sheet like this, Rollins?
Yeah, I cannot find that.
Do you think you have it somewhere?
Yeah, I know I have it somewhere. It might not be.
Okay.
The stuff I brought.
All right. I usually make 2 extras of everything. So on this table over here, if you want one, on this right at the end of this table right here. Now, again, the reason I don't like to do it the way a lot of science books or math books does it, they have 3 steps on how to put a number into scientific notation, and then on the next page they have 3 steps on how to take it out. Well, you better say, I better remember both pages. I better not mix them up. And I can tell you, if you use that lefty-righty thing, you're going to get let down. It'll let you down 1 time, 2 times, 10 times. So take a look over here, and take a look at number 1. Look right here. Tell me what kind of number that is. Is it 1 or bigger, or is it a decimal? It's bigger than 1, isn't it? Okay. So then I need to move the decimal 3 places. Now you say, which way? Which way do I move it? Wait, move it both ways. Move it left and right, and one of them will give you a big number. But really? Will that work? Try it. Which way you want to move it to make a big number? Let's go this way. No, it's getting smaller. And so you go, okay, move it 1, 2, 3. Wait, that was easy. I didn't have to remember left or right. You get it? And I think this is it puts you way above a lot of people. Almost lots of teachers will do that. They'll teach that lefty-righty rule, how to put it in, how to put it out, and then all of a sudden you switch around. Oh, not good at this stuff. Okay. All right. What do you think? Parker, which one did you do?
Oh, for the
What-
bottom one?
What number?
I did 6.
Okay, what's the answer?
I said it was 0.335.
And you know what? I knew when I saw that it was going to be a decimal number, didn't I?
Yeah.
And you had to move it 1 place, and when you move it 1 place, it's not going to be 33. It's going to be 0.3. See? That was easy. Make it that way. And you say, I can master this stuff. You'll never have to teach this to me again. If I go to college and that professor says you got to do scientific notation, you don't have to ask me. I got it. Let's move on. All right, Marie, which one do you do? Pick another one. 3. All right, what's the answer on that one?
0.0375.
Wow, that was easy, wasn't it? And I knew it was going to be a decimal number. You had to move it 2 places. We got it. You ready to move on? All right, let's go on. Now, what I'd like to do, I don't know if I did this in physics. I don't know if I did. Did we do this in physics?
Yes.
Okay. The reason I want to redo this is because you actually do this technique. You actually use this technique when we do a thing called spectrophotometry. What you're going to do is, on spectrophotometry, you're going to make a series of test tubes that you know the concentration. So what you do is you carefully make the stock solution, okay? You mathematically and weigh it out. You're gonna make this very carefully, and then we're gonna put that in the machine to see what reading it has, how much light gets absorbed. And then you're gonna make dilutions. You're gonna make careful dilutions of the stock solution and put that into the machine. Now what that's gonna give you is something like this. That's going to give you something that looks like this. This is called a standard. Now remember, that word standard means you know the concentration. You can be sure that's what it is because you made it, isn't it? A mass, a 1 kilogram mass is a standard because I trust that the company tested and everything. Get that? So when you make your own standard, this is called a standard curve, also known as a calibration curve. Now, what does that mean? Calibration curve means I would like to use this machine to tell me some unknown things. So I have to make some knowns. And so what you do is you'd make a known. Let's say, for example, this was a 1 molar solution. And then here you made a 10x, this is 0.1 molar, and this is 0.01 molar. And see that? And so if we were to make some things like this, and then we'd say, what is the absorption amount? How much light is being absorbed? Okay, so I made these solutions, and so you might get something like this. Well, let's pretend that it happens to be this. This is my best fit line, okay? Now this is what I'm going to use to find the unknown. This is a huge idea in science. You can find unknowns by comparing to the results you get from knowns. And this is big in science. I could take you all around the city and show people that they're doing this. So anyway, you have this unknown. You say, hey, what's the concentration of this unknown? Well, just a minute, I'll tell you. And we put it in the machine, and the absorption reading is this number right here. This is what the unknown comes out to be. Well, we go over here and said, you know what? You have the same absorption as a solution that I made that was 0.001 molar. You must be 0.001 molar. Does that make sense to you at all? So when I'm showing you this picture, maybe I'm just kind of, making it a little different last year in physics. But this is something you're going to do this year. And so I'm going to show this to you again. All right, what's a stock solution again? What would a stock solution be if you went to a chemistry lab and said, well, there's a stock solution, or what do you think?
Like a standard.
The standard, and it means I actually know the concentration of it, right? It's my starting point. Now, the one I made up for the handout sheet said, why don't we start off with a 5% acetic acid? If I go to the store and buy vinegar, you'll actually see on the package, it'll say, contains 5% acetic acid. Do you know 95% of what you're paying for is water? And the jar. But anyway, so this is called the stock solution. And so you would take the stock solution, and we would use pipettes. You could use pipettes, or you could be really, really careful with a graduated cylinder. What if I took 1 milliliter of the stock solution here, and I added 9 milliliters of water? Isn't that going to dilute it? And this is called, this right here, this saying, and first time I ever saw this was in college. No one ever showed this to me in high school, never. And it was called a 10x serial dilution. And this word serial means in a series. And so we're going to take it, and from here we're going to make the next one. From here we're going to make the next one. It's going to be in a series. That's why it's called a serial dilution. Now, why is it 10x? Look right here. 1 milliliter here, 9 milliliters of water. How many parts are in here? How many milliliters are in here now? 1 milliliter of stock solution, 9 milliliters of water. How many milliliters are in here now? 10. 10. Of the 10, how many are original? Look right here. Look right here. How many of these are original? Of the 10 pieces I put in here, how many are original? Out of 10. So what that means is this solution here is only 1/10 of the concentrations that was here. If this was 5%, then what is this going to be? This is power to 10 too. What is it? 0.5. Get it? Now, another way of saying this, it's 1/10 as concentrated as a stock, or you call it a 10x dilution. It's been diluted 10 times. Okay, so when I first heard this, I didn't know what they were talking about. I knew math, but I never seen this kind of stuff. Now, we take 1 milliliter of this and 9 milliliters of water. Now, guess what? This is 1/10 of the concentration of what? Of this? Of this, right? But if it's 1/10 of the concentration of this, then this would be what? This powers of 10 again. How concentrated would this be compared to the stock solution? What do you think? Lindsay, you do it. If this is 1/10 of that, and this is 1/10 of that, then tell me, how does this compare to that? And don't say 1/20. It's powers of 10. It's not. What is it?
100.
Yes. This is 1/100th of the concentration of the stock solution. Now, if the stock solution was 5%, this is 0.05. See, 5, 0.5, 0.05. Yes? So if you want to do an experiment, you said, well, I want to know at what percentage will this stuff make seeds not germinate? So you get a bunch of seeds, you put them in a petri dish, you get 20 random seeds, you put that in there, and what? You watch, and none of them germinate. 0. All right, that's too concentrated. See that? Seeds don't like 5% acid environment. Now you make another petri dish. You put your 20 random seeds in there, right? And here, no, none of them germinate. None. Next, you put them in here, 20 seeds. You say, oh, hey, two of them germinated. 2 out of 20. Okay, they don't like this. They don't like 0.05, but at least 2 of them germinated, didn't they? And then you go down here and you see you have 220 seeds in there. And what if like 10 of them germinate? Ooh, it's not bad, but all right. And what about here? What if we get to the point where 18 of them germinate? Okay. Now you know what we haven't done yet? What have we not done? What have we not done? Is this good or bad? Is this do seeds like this environment? You say, well, 18 out of 20. I don't know. I don't know. It's still not that good. How do you know? What have we forgotten? Marie, what should I have done before I put these seeds in there?
Like a control room?
Yes, I should have done a control petri dish. Now, what does that mean? In a control petri dish, I have no acid. Get it? No acid. So then, what if I put 20 seeds in there and 18 of them germinate? You see, I know what you're thinking. You're thinking every seed germinates. It doesn't. Get a package of seeds and start growing them. They don't grow, do they? Not all of them. So anyway, what if the control shows about 18 seeds germinating and we got 18 here? What would you say? Say, well, then this level of acid is okay for the environment. And who does that? What big organization and federal organization has to do with how much you can allow, how much lead can be in the water, how much, what is it?
FDA?
Even though they have a lot to do with food and stuff like that, who is it that makes standards?
The EPA?
The EPA.
Oh, I would
Now
never.
the EPA, the Environmental Protection Agency, they have hundreds and hundreds of scientists, and they do things like this. Hey, what do you think? What level of phosphates is allowable? And it's as if it's not there at all. It would cost way, way too much to take every chemical out of water. Do you understand that? You do not drink water that has everything taken out of it. It would cost too much. But we also know that if there's lead in the water, the level of lead has scientifically been shown not to affect living organisms. So we're okay with that. We say we're okay with that level. Does that make sense to you? I don't know if I can find it or not, but I will look for it. Once a year, the city of Greensboro. Yes.
Since we found this
What
worship
now?
team for the chapel.
Okay. Once a year, the city of Greensboro sends me an update for the water quality of Greensboro. And I'm gonna see if I can find that for you. And they have a whole list of things like copper, phosphates, and it tells you what the levels is in the drinking water of Greensboro. It also tells you what level is acceptable for the EPA. And the EPA says as long as you're 4 parts per million or less, it's safe. And so the city sends me a thing that says our water is 2 parts per million lead. Well, it's safe. And okay, so does this make sense to you all? All right, so let's do this one more time. This should be the last thing we do today. Wait a minute, let's see what time. Oh, okay, all right, here we go. All right, stay with me on this. If this is 1/10, this is 1/100th of the stock. This is one what?
1,000.
All right, so it's 1,000th as concentrated. So if this was 0.05, this is going to be what?
0.005.
And what about the last one?
0.0005.
Okay, now, instead of being babies about this, we're going to be a little more grown up. This is 5 times 10 to the 0. This is 5 times 10 to the what? All right, this is 5 times 10 to the what? -3, 10 to the -4. Is that right?
Yes.
All right, so now we see this is where you get to be a good science student, okay? This kind of stuff. They don't even teach this in most schools. They don't even teach, I didn't even see it till college, but wow, it makes so much sense with powers of 10 and things like that. All right, what do you think? You okay on that? Let's ask some quick questions here. If you can answer these questions, you probably understand the lesson, all right? How many milliliters liquid are in tube number 3?
10.
What do you think? And I would have said 10, but it's a trick question because guess what? You took a milliliter out. So there's only 9. But anyway, that's okay. Say, all right. Anyway, so there's actually 9 here, 9 here, 9 here, and there's 10 here. Sorry, little trick. What fraction of the total volume of liquid in tube 1 is vinegar? What fraction of the total volume in tube number 1 is vinegar from the stock solution? Uh-oh, this is an easy question. 1/10, isn't it? Isn't it 1/10?
Is that our stock?
Yeah, in here.
Oh, yeah, that one.
Okay, next, number 3. How many times has the stock solution been diluted in tube number 4? Been diluted 10 times? And by the way, the people who do this, the first time I saw this was in a microbiology class in college, okay? And here's how they have a certain kind of lingo they use. That's a 10x dilution. Okay, I can understand that. 10x dilution, I got it. You know what they call that? 10 squared x. That's 10 squared x dilution. Oh, okay. 10 cubed x. What's this one? 10 to the 4th, isn't it? Wait. 10 to the 1st. It's been diluted 10 times, right? 10x dilution. 100x dilution. 1,000x, 10 to the 3rd. What's this one? 10 to the... Wait, hey, how am I losing this? 10 to the 1st, 10 to the 2nd, 10 to the 3rd. What's this one? 10 to the 4th. Okay, how much is 10 to the 4th? 10,000. Again, I'm trying my best. Just like a writing class, they're trying to make you better writers. I'm just trying to make you a better science student. You get that? And by now, if you had any gaps in here, you should be filling those gaps in. All right, next question. What is the acetic acid concentration found in tube number 4? 0.005%. Also known as 5 times 10 to the minus 4th, right? Percent. Are you okay with this? All right. So I'm not going to, we will cover this later. When we talk about light, this is a powers of 10 thing. When we talk about light, the electromagnetic spectrum has many, many, many wavelengths, and this is in meters. And so you got these really big waves, and you got these really tiny waves. And anyway, they're all in powers of 10. You see that? And so we find out in this little tiny section right here, in this really tiny section here, is visible light. And that's where you find the rainbow colors. And that's somewhere between 700 and 400 nanometers. So, and we'll be using that in another lab. 400 to 700 nanometers is visible light, but we do have machines that can look at light in the ultraviolet, infrared. If you become an astronomer, it's okay to look at visible light. It's okay, but most astronomers don't. That's been done. and they know what it looks like. So they're going to look at another kind of light, like maybe radio waves, and a part of space that may look very dull. You look at radio waves, it's like on fire. Wow, there's something really big going on there, because radio waves, they're long wavelengths, but it's like on fire there. Or they might look at the infrared. What's the infrared view of the heavens? You get that? So anyway, I just want, that right there is just something that has to do with powers of 10. All right, I think we're about done. Please, I would like you very much. I'm going to give you a paper, and I didn't know she was going to leave early. Our test is going to be next Thursday as of right now. I'm going to check to see if everything's okay, but this is a homework paper, and I want to set it clear. It's really, this is something that you have to maintain. You have to say, I'm willing to maybe spend maybe half an hour every other night, and I can do that. And so what you do is, says they get credit. I'll give you credit for this. To get full credit, answer the non-multiple choice questions, and if there's work to be shown, you have to show your work. And then what happens, we go down to the, let's see what page here in a minute. We'll be doing some of this more tomorrow. Look over there, find the multiple choice sections. Have you seen it? There you go. Now there, you don't have to show your work. You can if you want, but I require you to show your work on the other ones. So now, what do I want you to do? To get full credit, when you turn your homework in, on the multiple choice, you have to write your answer there, like A or B or C, and then I will give you the answer key. I will give you the answer key probably on Tuesday of next week, maybe Wednesday, and then you will grade your little quiz. So the multiple choice is almost like you're taking a practice test. And then all you do is grade it. You don't get a lower homework grade. If you miss 10, that's okay. That doesn't bother me. It should wake you up and say, wait a minute, I missed 10 of these. I better go back. So one more time, to get full credit, tells you what you have to do on a separate sheet of paper. And when you do the multiple choice part, I'll give you the answers. And all you do is grade it and show how many you missed. And you will not get a lower grade if you happen to miss a lot of them, right? What I don't want to see is just the multiple choice answers written down and it wasn't graded. And I'm not stupid either. I really got behind on my homework, so you could do it. You're only lying to yourself. And I get it. I didn't miss any. Oh, good. You should get a good grade on the test, then, shouldn't you? Hey, have a good day, and thank you very much. And
When is this due?
Tuesday, so I do on the day of the test, and so that would be a week from Thursday. I'll give you the answers, like I said, maybe next Tuesday or the worst case scenario, Wednesday.